Hi and welcome to this Leaving Cert Applied Maths video. Today we're looking at finding the shortest path using Dijkstra's algorithm. So when we talk about shortest path, what we're talking about is the shortest route to get between two nodes. And although we talk in terms of distance, these numbers can talk about costs or time or anything like that. The big difference here between shortest path and our minimum spanning tree is that the minimum spanning tree connects all nodes, while for us, when we're working with a path, we're not talking about every single node, and we're talking about only the ones that will make the route as short as possible. So here I've just put up a picture of a network, and in red we can see this shortest path. There are nodes that are never visited, and that is absolutely perfect. So when we talk about Dijkstra's algorithm, we're working with that shortest path. So we're trying to find our shortest paths forward. And basically, we're going to use what's called like a list or table method. This is exactly the same as working on the graph. The only difference is I put my workings to the side. One of the reasons I think this helps is because students often miss things, or on the graph it's very busy anyway, so they tend to make a mistake because they can't see their work. So it is worth just maybe working off the graph a little bit so you can really clearly see your work. In some of the books, there are layouts on the graph that won't be given to you in an exam, so it's important that you're either working in the way that I'm going to show, or you're putting this information on your graph. So how I'm going to start is with the given node. I'm then going to list all the other nodes that are connected to it, and I'm going to put their distance, and that's the total distance, in the brackets. I'm going to pick the next smallest bracketed value of my working nodes. That becomes my next like locked in or live node. And then I continue that until I get to my destination. Usually we'll end up with all of the nodes completed before that. And once we have that, we're going to find our way backwards. So we trace back our shortest path. So the key idea here with Dijkstra is that it picks the closest unvisited node, ensuring that the shortest known path ensuring that the shortest known path to that node is always correct, and it builds the shortest route gradually, one step at a time. So let's take a look at a nice straightforward example just to get us started with this algorithm. So this is question 4, part B from the 2023 ordinary level paper. Mark is planning to visit South America. He plans to begin his visit in City A and then travel across South America to meet some friends in City I. Mark wishes to keep his travel cost to a minimum. He wishes to calculate the cost of traveling to City I by bus, by traveling via some other cities, B to H. The cost in euro of traveling by bus between the various cities is shown in the network below. Mark does not intend on visiting all of the cities in this network. Use Dijkstra's algorithm to find the cheapest bus route from City A to City I and calculate the cheapest route. Relevant supporting work must be shown. Okay, so here is our little graph. And I'm going to create this table. Now, the reason I use a table is I am working on a white page, and it just keeps me within the lines, really. But if you are working on the square paper given to you in the exam, all you need to do is to make a column for the first node, and that's it. So we are trying to get from A to I. So here is my start node. So we lock that in straight away. So as soon as a node is written on the left-hand side, it's locked in. I show this on the graph by circling it, and you can label that node 1 if you like. There's no real need to number your nodes. It's not going to add any huge value. But if you want to kind of keep track of it, we can. Then we look and say, well, what is A connected to? So, actually, the reason there's a 0 in the bracket is because we're always calculating these distances from the start. A to the start, which is A, is no distance. So then it's connected to C, which is a distance of 105. It's connected to D, which is 84, and it's connected to B, which is 75. So we look at the nodes on the right hand side of that thick line, so where it says connected to, and these are called my working nodes. So these are all ones that we're currently working with. These are working values. Nothing is set in stone. And we choose the next smallest number. So our smallest distance is going to come from B, and it's 75. So as soon as we use that, I put a box around it. This node now becomes locked in as node 2, and I circle it on my graph. So then we look at all the nodes that B is connected to, and there's D. Now B to D is 60, but we already have that 75 there. So we have to keep a total distance, okay? So those brackets show us our total distance. We also have B connected to E, which is 99. So that gives us 174, and that's it. B is connected to A, but that A node is already locked in, so we can't revisit it. Within this table, then, you can see that actually we have two ways to get to D. We have an 84 and a 135. Because we're looking for the shortest path, we get rid of any duplicates by getting rid of the bigger values. We now have three working nodes, C, D, and E. The next smallest node is D. One common mistake that I see on these is students tend to work the nodes in order, so like A, B, C, and so on. That is not exactly how it will work, so just be careful not to assume that the nodes are going to go in order. So now that I've locked in D, I have to look at all the nodes it's connected to. It's connected to C. C has 49. And when we add that to the 84, that gives us 133. D is also connected to F, which is 135, and that gives us a 219. Now, D is already connected to B and A, but they're locked in, so we're not going to include those. We have another duplicate situation with this C, so we're going to cross out our C here, and we're going to look at the three working nodes that we have left. We have C, we have E, we have F. So let's take C. It is the next smallest value, so C gets locked in as node number 4. So that is C, which is 105. C is connected to G, which is 87, which gives us 192. And that is it. So we have C connected to A and D, but they are already locked in. So we have three working nodes. We have E, we have F, and we have G. So we're going to lock in our E because it is the smallest number. So that's E is 174. So this becomes node number 5. And E is connected to F, which is 50, so that's 224, and H, which is 122, and that's going to give us 296. We have a duplicate now. We have two values for F, so I'm going to get rid of that bigger one. And our next smallest node is going to be G. So G gets locked in as node number 6. So G is 192. So G is only connected to I, which is 188. So if we add 188 and 192, we get our 380. Now, don't get too excited. We have got to the end, but these are only working values. It doesn't matter when you get an I in there. Until it's locked in, we don't stop. We keep going. So our next smallest working node is our F, which is going to be 219. So F here is 219. This is node number 7, and it only connects to I with 111. So that gives us 320. We now have a duplicate of I, so we get rid of our bigger value. So then our next smallest node is H. So that is 296. It becomes our 8th node locked in. So H is our 8th node. And the only thing you can do from H is to get to I, which is 48, which is 344. We have a duplicate of I, so we get rid of the bigger one and we lock in our I at 320. So that is our final step. So there's our node. I know I've kind of blocked it with my numbers. So there's 2. So I is node number 9. So we're asked to find the cheapest route, and the cheapest route will be 320. But what is that actual route? So let's follow our table back. So I320 is exactly what we need. Go back up to where we had it boxed, and it came from F. Go back to where we had F boxed, and it came from D. Go up to where we had D boxed, and it came from A. So that means we were going I, and it came from F. F in turn came from D. D in turn came from A. So our actual route here is A, D, F, and I. And sorry, I actually just realized this should have been 330 for both of these. Doesn't change our path. So here's our 330, which is our final answer. So sorry, F to I was 111 plus 219, which should have been 330. Doesn't change our work through, but it does give us a different answer. So will Dijkstra's always work? And the answer is no. Dijkstra's won't work. It will fail as an algorithm when we have negative edges. So let's take our, just a very simple graph here on the left. I know you can probably do the shortest path here in your head without any major work, but our focus is on Dijkstra's algorithm. So I need you to really, really think like a computer and follow each step of the algorithm and not kind of adjust it based on what you think. You're focusing 100% on the algorithm. We're going to go from A to F. So let's start with node A. That's our first node. And A has a distance of 0, but it's connected to B, which is 3, and C, which is 3. Doesn't really matter then which one you decide to do next. I'll just do them in order. So there's B, so B becomes node 2. So if B is 3, that gets us to C with an extra 5, so that's going to be 8. But we already have cheaper, so we cross that out, and then we work with our C, so that becomes node 3. So then C is 3, C connects to D with an extra 4, and E with an extra 5. Our next smallest number then is D, which is 7. And then that locks in as node 4. And then we can't connect D to E because the arrow is showing us going the other way. So the only one that D connects to that isn't already locked in is F, and that gives us, an extra 1, which is 8. And then it doesn't really matter which way we go, so we'll go E, which is 8. So that's node 5. The only one it can go to is F, which is an extra 3, which is 11, which we're not going to have. So our final answer is F, which is a distance of 8. So if we look at that, this is our final one, F, and it came from D, so we connect here. D came from C, and C came from A, and that is my shortest path, which is 8. However, and you may have figured this out, there is a shorter way that we could have worked. We could have gone here, that's fine, but if we had gone to E and then D and then F, we would have had a slightly smaller answer because we would have had 3 plus 5 is 8. Take away 2 is 6, plus 1 is 7. So we actually would have done it quicker. So the issue around negatives is we lock ourselves into a node in Dijkstra's. It's a greedy algorithm. So the fact that a minus comes along and gives us like a better answer, we've already locked in. We've been greedy. We've made our decision. We can't look ahead and go, oh, but that minus is going to do that because that goes against what Dijkstra's algorithm is. So when we have negative edges, we can't use Dijkstra. So we need to have an alternative. And that's where Bellman's comes in. Now let's take a look at question 2, part A from the 2023 higher level paper. And this question looks at Dijkstra's algorithm. So we're told that a university wants to improve the paths on campus. We're given this diagram below. X and Y are entries and exits to the campus, and then all the other letters A to N are buildings of importance. So they want to redo the pathways, but rather than redo all the pathways, instead we're going to look at the shortest path. So in the last paragraph, it tells us the university decides that the first part of the work will provide an improved route between entrance X and entrance Y. Use Dijkstra's algorithm to find a route between X and Y that is cheapest to improve. So our numbers in this case represent euros. So when we're working with this, and we're working with Dijkstra's and the shortest path, the main difference is we're not trying to connect all the nodes. What we're trying to do is to get from X to Y, going through as many or as few nodes as it doesn't really matter. Really what we're focusing on is we want this to be the shortest path possible based on those numbers. Now, in the books with Dijkstra's algorithm, there are sometimes a format laid out on the graph that you can work on, which are lovely. However, in an exam, this is what you're given. So I'd strongly recommend not to focus on that layout because you're not going to have it in the exam. You can work on the graph. However, at higher level, when we're working on these graphs, they're quite busy anyway, so there's not a lot of space to work. So I'm going to use the same logic, but I'm actually going to use the table method, which just records all those working values in a table rather than on the graph itself. And what I find is students who use the table method, they're less likely to make errors. They can really see their work. They're not as likely to make a mistake. So for us to use the table method, I just set up a little table like this. You don't need to even set this up. You can literally just put your nodes on the left. That thick black line is helpful, so use some kind of separator. I'm using a box to kind of keep me in line on the page, but you will have square paper when you're working. I'm still going to work on the graph as well, and you're going to see how we're going to label our nodes as we go. So we're going to start at entrance X, and that is node 1. You can call that node 0 either, it doesn't really matter, but I'm going to call this my first node. So when I work with X locked in as my first node, I need to look at all the nodes that are connected directly to X, and they are A, B, and C, and the values are then given in the brackets. The next node we choose is the smallest value of these. So that for us is going to be C, and that locks in C as node number 2. So I'm just going to circle it and label it. So all I'm doing on my graph is circling and labeling. All the working values and final values are going to be in my table. So then I look at C, and it's connected to B and F. So when we're doing our distances, but they're not distances, they're money here. But when I'm getting my total value for B, I have to take into account X to C plus C to B. So when I go to B, it's going to be 1,250 plus the 900, which is the 2,150. Why it's helpful to have those values in the brackets on the left-hand side. For F, it's going to be 1,250 plus 3,900, which gives us 5,150. This point, you can see we have two ways to get to B. We can go from X to B or C to B. However, we always want the smallest value, so I'm just going to cross out the bigger value here of B. I have 3 working nodes, so that means A, B, and F all have a working value. I want to choose which is the smallest. That is going to be B, 2,150. And then B gets locked in as node number 3. So then from B, I can go to F and to G. So F is going to be 2,150 plus 2,150, and G is going to be 2,150 plus 4,200. Now I have A, F, and G, but there are actually 2 working values for F. We have from C to F and from B to F. I want to take the smallest, So I'm just going to cross out this 5,150. We have A, F, and G, and the smallest value of those is going to be A, and we lock that in as node number 4. So then looking at A can go to E and it can go to D. So we get E 4,200 and D 6,050. We've no duplicates here. We have F, G, E, and D. Our next smallest value of all of those is going to be E, and that gets locked in as node number 5. And E only goes to D, so that's 5,950, which is smaller than the current value we have from A to D, so we're going to cross that A to D out. We now have 3 working nodes, F, G, and D. Our smallest value of those is going to be F, so F gets locked in as node 6. I like being able to see on my graph which nodes have been locked in and their order. I'm happy with all the other working then to be on the table. So from F, I can go to H and I can go to I. So H will be 5,900. I will be 6,500. So keep an eye on what hasn't been used yet. I have G, I have D, I have H, and I have I. So my next smallest value is actually H, and that is going to be 7. That G on line 3 up above, don't forget about it. It's there and we will probably have to use it or get rid of it at some point. So be very clear about where you've used values and where they haven't been. Sometimes students, instead of this red box, they like to use a highlighter. That's absolutely perfect. So once it's very clear to you which nodes are still in the working value phase. So from H, we can go to G and we can go to I. And then we now have 2 values of G and 2 values of I. So for G, we're going to pick the one from B to G because it's smaller. So I'll get rid of this one. And from I, we have F to I and H to I. F to I is smaller, so we're going to get rid of our H to I here. So then our next smallest value of G, D, and I is D, and that gets locked in as node number 8. So then from D, I can go to J and I can go to G. So there are my 2 values. I get G is 6,600 and J is 8,950. I have 2 G's here. So again, keep an eye. Let me just highlight this one. So we have a G up here that hasn't been used. So these are our current working nodes. So the G's, I have 2 of them. So I'm going to get rid of this one because we do have a smaller one. And now this G here is our next smallest value. So this is our node number 9. So I'm going to lock that in as node 9. From G, I can actually only go to K. And that will be 8,850, and I don't have another K on the board, so that's fine. I now have I, J, and K. The smallest value of those is going to be my I, and that becomes node 10. Okay, so when I look at I can go to K and I can go to L. Now, interestingly here, there are 2 values of K that have the same, well, they're the same number. So you can go to G to K or I to K, it's going to be the same. So I suppose I'm going to show both of them. It's worth, in case this is going to be something in our answer, it is worth kind of just flagging this for yourself with like a highlighter or a star. But for the moment, all we care about is getting that value into the table. So I'm just going to put K 8,850 here. Right now, it doesn't really bother me where it's coming from. I know I have those 2 options. So when I'm working back to get my pathway, then I will deal with that if I have to. Remember, we work through all the nodes here, but the shortest pathway won't include all the nodes. So this becomes node number 11. So I lock K in as node 11. That means we have L, M, and J. And then we now have 2 values of M. So we get rid of the bigger one here. And we have 2 values of J. So I'll get rid of that bigger one there as well. The next smallest value then is our J. and that gets locked in then as node number 12. So there's J getting locked in as node 12, and J only goes to M. We do already have a value of M, but that's bigger, so we'll get rid of that value of M. So we now have L and M are working nodes. So the smaller value of those is L, and L gets locked in as node number 13. So L can go to two nodes, that's Y and N. They're all new nodes, so we don't have anything to cross out. We now have three working nodes, M, Y, and N. We are going to take the smallest value, which is M, and this gets locked in as node number 14. And then from M, we can only go to Y. This gives us a smaller value of Y than we currently have, so we'll cross this out. And then that is actually our end point. So this becomes node number 15. Y is the node we want to end on, so that's perfect. If we want to go a step further, M becomes 16. So how we then decide on our pathway. So this is our final answer. We're going to get to Y in 11,450, and that's the smallest value possible. So how we decide on our pathway is this. So this is our value of Y we want, and it's come from M. We then go up and see where that M was boxed, and that's why the boxing or highlighting is so important for us. So M then came from J. We go up and find the J that was boxed, and J came from D. And then we go up and find D that was boxed. It came from E. The E came from A, and A came from X. So that's my pathway. I went X to A, then I went A to E, then I went E to D, then I went D to J, then I went J to M, then I went M to Y. So that's how you work backwards in the table method. So we can show kind of the working backwards. So going from the bottom of the table up, it went Y to M, M to J, J to D, D to E, A to X. But the actual pathway, make sure you flip it to start the other way around. So it goes X to A to E to D to J to M to Y. It is helpful to kind of draw it on the diagram as well. And our total value for that was going to be 11,450 because it did ask us to calculate the cost. So working on the graph is absolutely fine. You can do the exact same workings as we did there. This question in particular, the numbers are quite big. Often when we have thousands, we're given the smaller number, like we're given 2 and then the 1,000 isn't written, and then that's a little bit easier to work with on the graph. These big numbers are tricky. So I like this table method. It's a nice way to do the same method, but just give yourself space to work. Often when your work is like squished in, that's where mistakes happen. That's where silly adding things happen or you miss something. So this is a really lovely method for just giving the data its space and giving you the space to do your work and to think, and you won't be as prone to error. So this is question 2, part A from the 2023 deferred higher level paper. 7 computers, A, B, C, D, E, F, and G are part of a computer network. Each computer is connected to one or more of the other computers on the network. The time in milliseconds for the communication between each of the connected computers is given in the table below. A computer scientist wished to model this information using a weighted graph, where the nodes represent the computers A to G, and the weights of the edges represent the communication between the connected computers. Use the table above to draw a weighted graph to represent the computer network. So this is what our network would look like. So I go through that in a little bit more detail in the networks and graphs video, which I've linked in the description below. So part 2 asks us to calculate the shortest time for a message to travel from computer A to computer G. List the computers, list list the computers that the message travels through in order, name the algorithm used, and relevant supporting work must be shown. So we're going to use Dijkstra's algorithm for this, and we're going to work in the same way. So we're going from A to G, so let's lock in A as 0. A is connected to 2 nodes, B which is 42 and C which is 33, and C then becomes our next node that we're locking in. So there's our node 1, C becomes our node 2. So C is 32. C is connected to B with a total of 52. C is also connected to E with 137. It's also connected to F, and that is 33 plus 78, which is 111. However, we are not going to use this B because it's too big. Our next smallest value is our B, which is 42, and that locks in node 3. So node 3, that's B, and it's 42. B can then go on to D, which is an additional 54, so that is 96. That's all that it can do. So our next node now is going to be D. So D locks in as node 4, and that is 96 total. And D is connected to E. Although it may feel like we're kind of going backwards there, it can flow both ways. So as long as it's connected, it's fine. So we've 1, 2, 5. And then we also can connect to G, which is 190. So then E has a duplicate, so we get rid of the bigger value. And then our next smallest node is going to be F. So 5 is F, which is 111. This locks in as node F. F can go to E, and that gives us 152. It can go to G, which is 182. Now we have some duplicates, so we have to get rid of this E, and we're going to get rid of that G. Our next smallest node is then our E. So let's lock that in. E is going to become node 6. And E has a total of 125. E can then only go to G, which is 174. Now we have a duplicate, we get rid of that, and we lock in our G. This is going to give me 7. G is 174, and we're now locked in. So that is our final answer for our G. G came from E, so we went G to E. E came from D, and D came from B, and B came from A. So our path is A, B, D, E, G, and it has a total of 174 milliseconds. So this is question 5A part 1 from the SEC sample higher level paper. In the network shown below, the edges represent roads and the nodes represent the junctions of 2 or more roads labeled with the letters A to N. The weight of each edge represents the distance in kilometers between a pair of junctions. Use Dijkstra's algorithm to find the shortest path from junction A to junction N. Calculate the length of the shortest path, and relevant supporting work must be shown. So we're going from A to N, so let's set up our table. So let's go with node number 1 as our starting node. That is 1. Sorry, that is A. So A, and it has 0. So A is connected to B, which is 17, C, which is 12, and D, which is 25. So we want to lock in the smallest value, so that's going to be C. So C gets locked in as node 2. So C is 12. So C is then connected to D, which is 23 total, or G, which is 35. We now have a duplicate for D, so we're going to get rid of the bigger value. And our next smallest working node is going to be B, and we lock that in as node 3. So we get B, which is 17, and that's node 3. So B then can connect to D, which is an extra 9, so that gives us 26, and E, which is 27. We now have another duplicate of D, so we have to get rid of the bigger value, and we work with our next smallest node, which is D. D is going to lock in as node number 4. So D is 23. D is connected to G, which is 24, so that's 47, and F, which is 8, which is 31, and E, which is 14, which is 37. We now have duplicates for G, so let's get rid of the bigger one, and for E, let's get rid of the bigger one there too. So the smallest working value we have is E, so E gets locked in as node 5. So we have E, which is 27. E links to F, which will give us 39, and H, which is 27 plus 18, which is going to give us 45. We now have a duplicate for F, so we're going to get rid of that bigger value. So we now have 3 working nodes. We have F, we have G, and we have H. So let's take F, so that's 6. So F is 31, and this is my node 6. So F is actually only connected to I because all the other nodes it's connected to are already locked in. So we now have G, we have H, and we have I. So the next smallest node we're going to put in is G, and that is 7. So G is 35, and that's linked to J, which is 35 plus our 19, which gives us our 54. We have G to I, which is our 35 plus 15, which gives us our 50. We now have duplicates of I, so we get rid of that bigger value. Our next smallest node to work with is our H, so H gets locked in as node 8. So H is 45. H is connected to I, which is 21, which gives us 66, and K, which is, H to K is 16 plus 45, gives us our 61. We now have duplicates for I, so we're going to get rid of that bigger value. I is now our next smallest node, so that's going to get locked in as node 9. So we have I is 50. So I can go to J, which will give us a total of 62. We can go to L, which will give a total of 63. And that's it. All the other nodes it's connected to are locked in. So J has a duplicate, so we'll get rid of our bigger value. And the next smallest value then is that value of J. So J is 54 and node 10. So J 54. We have M, which is 61. We have L, which is 60. And that's it. We now have a duplicate for L, so let's get rid of that extra value, the bigger one. And we're going to work with L is 60. So L is 60, gets locked in as our 11th node. So then L can connect to M, which will give us 69. It can connect to N, which is 72, and it connect to K, which is going to be 64. So we have some duplicates here. So we have M, we're going to get rid of the bigger one. We have 2 for K, and we're going to get rid of the bigger one. Now, we have two values that are the same now. We have K and we have M. Doesn't matter which one we're coming from. Or which one we deal with first. If we're coming back through them, this could in theory give us 2 shortest paths. However, we won't generally see that in an exam question. So it doesn't matter which one you pick to go first. So I'm going to just pick K. So we have K is 61. So I'm locking that in as node 12. So there's my node 12. And then the only thing that K can link to is N. So that is plus 15. So that's going to give us 76, which is, we already have a smaller value. So let's get rid of that. So then our next one is going to be M. I link this in, or I lock this in as node 13. So M 61. Then it can go to N, which is going to give us 75, which again is actually too big. So we're just going to cross that out. And then absolutely last but not least, we get node N, which is our node 14 that we're locking in, and we get N is 72. So our answer here is 72 kilometers. So that answers the length of the shortest path, but it asks us also to find that shortest path. So let's go back through this. So we have N, which is 72, and go up until you find it boxed. You might decide to use highlighter and cross them out to make it easier to see. It's completely up to you. So N connected back to L. So we go N to L. We go back here to L, it came from J. So L came from J. And then J came from G, and then go up till you find G came from C, and then C came from A. So we get, for our final answer of our path, A, C, G, J, L, N. So A, C, G, J, L, N, and the length was 72 kilometers.